Okay, Chapter 8, Section 3, Geometric Sequences.
Okay, so in this section, we'll cover what is geometric sequences, an introduction, an explanation of what is geometric sequence. We'll look at partial sums of geometric sequences, and what is an infinite series, define what that is, and then figure out what the infinite geometric series are. Okay, so again, establishing a nice little pattern for them. Okay, so geometric sequence. So we looked in general of what is a sequence, right? A sequence is just a series of numbers, a list of numbers, where the order matters, right? That list could be anything. Right, so a sequence, a sequence is just any list of numbers. It could be anything like 3, then 5, then 7, then 9, then 11. Okay, so it looks like I'm listing the odd numbers. That's a sequence. It could be something where I'm squaring it and subtracting 1. So maybe I start with squaring 1, subtracting 1, we get to 0. Squaring 2 and subtracting 1, we get to 3. Squaring 3 and subtracting 1, we get to 8. Squaring 4 and subtracting 1, we get to 15. Okay, so here's another potential sequence. Good. It could be a sequence of decimals. It doesn't just have to be whole numbers. We tend to stick to a lot of whole numbers or simple fractions just because it's easy to work with them by hand, right? But a sequence could also be decimals. It could be something like 0.31, then 0.031, then 0.0031. Okay, so here's another term. Okay, so here's a potential sequence. These are all sequences, and they all have some sort of pattern to them, but they don't have to have a pattern. A sequence could just be a list of numbers, and maybe it's random chaos. Maybe the first number is 0.2, the next number is 17, the next number is negative 3.19, the next number is 0, the next, right? There might not even be a particular pattern, and that's still a sequence, right? It's just a list of numbers where the order matters. This is the first number, the second number, the third number, the fourth number. Okay, but of course, if there is no pattern whatsoever, there's nothing really interesting you could do with it, right? It's just a list of numbers, okay? Where we can have some fun is when there is some sort of an established pattern, a closed formula that can predict the next one, or a recursive formula that can predict the next one based on the ones that came before it on the list. So one common pattern that we already worked with was arithmetic sequences. Remember that an arithmetic sequence was a sequence where we always add or subtract a constant value to get to the next one. So for example, this one qualifies an arithmetic sequence. The odd numbers starting at 3, I didn't start at 1. The odd numbers starting at 3, look, we always add 2 every term. That's an arithmetic sequence, right? To get to the next one, we add 2. To get to the next one, we add 2. To get to the next one, we add 2. Right? So this happens to be a sequence that fits a particular pattern, an arithmetic sequence, and so we worked with those yesterday. Okay, so another common one is geometric sequences. Geometric sequences is going to be a sequence where there's an established pattern, and the established pattern is that we always multiply by some common value, a constant value. So for example, if we start off with any random number, let's say we start off with the number 5. Okay, so we start off with some number, and to get to the next one, we always multiply by the same thing. So let's say it's just 2, so that if we multiply by 2, we get to 10. If we multiply by 2, we get to 20. If we multiply by 2, we get to 40. Multiply by 2, we get to 80, and so on and so forth, and so on and so forth. Good? So to get from one term to the next, we multiply times 2 to get from there to there, right? And multiply again by 2 to get from there to there. And then we multiply again by 2 to get from there to there, right? So we have some common starting value, which we call A, and then to get to the next one, we multiply by the 2. So this 10 over here can be rewritten as 5 times 2. Good. And then to get to the next one, we multiply this one by another 2. So it's 5 times 2 times another 2. Right? Because this is 10 times 2 gets to 20. Right? Or we can relate any one of these numbers as the initial value times a certain number of multiples of 2. Good. Okay, so here is the official description of the geometric sequence. So a geometric sequence is a sequence of the form A times, A is the first term, then the next one is AR, then the next one is AR squared, then the next one is AR cubed, and so on and so forth, so on and so forth. Good. And notice that there is a pattern between its location and the number of times that you multiply R for that term. So going back to this thing, this guy is, let's put it in blue. This guy was just A, okay, so there's nothing there, that's just A. And then A sub, well, this is A sub 1. It's the first one on my list. right? It's just that guy. A sub 2 is this guy. A sub 3, the third one on the list, is this guy. And then this guy is going to be A sub 4 is going to be the number that comes there. And going back to establishing the number of times that we multiply by 2, this one's going to be A times, and there's going to be 1, 2, 3 copies of 2. Good. So if we notice a pattern between the number, starting with this one, the number of times that we multiply the common value r and its location, right? So the second one on the list, we multiplied 1 copy of 2. The third one on the list, we multiplied by 2 copies of 2. The fourth one on the list, we multiplied by 3 copies of 2. So there's always one less, right? So in other words, if I want to jump down the list here, dot, 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 and I want to figure out what is A sub 17 going to be. Well, following this pattern, I know, kind of going in reverse, that it's going to be a 5 times 2, and then the 2 gets repeated several times. It's going to get repeated 16 times. Times 2, times 2, times 2, times 2, dot, 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 dot. Another 2, there's going to be 16 of these. 16 times. Is that okay? Following this pattern. All right. There's 1 copy of 2 there. There's 2 copies of 2. Good, good, good. Okay, well, then in that case, I'm just going to rewrite this using exponential notation and say that my list of, it's getting kind of messy, so I'm just going to copy it down here and do it one more time. 40, then 80, dot, 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 dot. Okay, so I can rewrite this as a 5, rewrite this as a 5 times 2, that's 10, and then 5 times 2 squared, because that's going to be 4 times 5, that's 20, then 5 times 2 to the power of 3, that's 8 times 5, that's 40, and then 5 times 2 to the power of 4, that's 16 times 5, that's 80, good. And again, if we put a little 1 there, and then we think about its location on the list, the first number on the list, the second number on the list, the third number on my list, the fourth number on my list, the fifth number on my list. So what I was pointing out over here is that the little exponent on my number 2, the little exponent, is always 1 less than its location. Right? So like over here, if I skip down the road there, and I got all the way down to the 17th spot, the 17th number on my list, I can establish, based on this little pattern, that that number is going to be 5 times 2 to the power of 16. And then in general then, if I keep going, dot, 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 and I just want to know what happens in the nth spot. The nth spot on my list, well, following this little pattern, it's going to be equal to 5 times 2 to the power of, and it's always 1 less than its location, so it's going to be to the power of n minus 1. Good. All of this was just one unique example that I just happened to pick out of nowhere, right? It's just a random example. And this is an example where the base initial value A is a 5, and I just randomly chose R, the common multiple, the common ratio, to be equal to 2. Good. Good, good. So if we take that into account, then this, from here, we can see that the general formula is going to be A, what you start off with, that initial amount there, times R, that common ratio that you constantly multiply, to the power of n minus 1, right? That's equal to a sub n. A sub n is equal to this. Remember that a sub n is just another formula for a function. It's another form of expressing a function. A of n is equal to a times r to the n minus 1. It's another equivalent way of saying it. Or, we're really used to writing functions with an f, so if you want to write it as f of n is equal to a times r to the n minus 1 power. Right? These are all saying the same thing. It's a function where you plug in n, and the output would give you the value in that location on your list, in the nth location of the list. Any questions about any of this stuff over here? So then let's go back over here to the official definition. An arithmetic sequence is generated when we repeatedly add a number d to the initial term, right? A geometric sequence is generated when we start with a number a and repeatedly multiply by a fixed non-zero constant r. Okay, so here is a generic list of the first few terms of our sequence that fits a geometric pattern. Right? The first term is a, r is the common ratio, and the nth term is described by this formula. Okay, so the number r is called the common ratio because the ratio of any two consecutive terms of the sequence is r. So if you were given a sequence and you wanted to figure out what r is, then if you can find two consecutive numbers, then you divide them. You divide them and you'll find that common ratio. Okay, so let's look at some examples of geometric sequences. So here's an example where a, we start off with 3, and the common r value is 2. So we start off with 3, and then to get to the next one, we multiply by 2. And to get to the next one, we multiply by 2. And to get to the next one, we multiply by 2. Right? So we're constantly multiplying by 2 to get to the next one on the list. And then, of course, we can actually multiply them, and here is another way of expressing the same sequence. 3, 6, 12, 24, 48, and so on and so forth. Right? Notice that if this was the thing that was given to you, right? If this is on the next exam, here is this geometric sequence, find the value of r. How can you get that? Well, if you just get any two consecutive numbers and you divide them, right? Like 24 divided by 12, you'll get a 2. Right? Note that 24 divided by 12 equals to 2. Or 12 divided by 6 is equal to 2. Right? Or any of them. 48 divided by 24 equals to 2. So that's one way to go backwards. And well, if this whole thing was given, then it's easy to tell what that first value is, that initial value of a. Or even if the first ones were missing, we can work backwards to find it, right? So on the next test, maybe I give you blank, comma, blank, comma, blank, comma, 24, comma, 48. Even if I only gave you this much information, and I said find the equation of this geometric sequence, it would be important to point out that it's a geometric sequence so that you understand the formula, the general form of the formula that applies here. So even by just giving you these two terms, we can use this idea to find r, right? R would be 2. So if you multiply by 2 in this direction, that means that going in the opposite direction, we divide by 2, right? So going this way, multiply by 2, multiply by r, which is equal to 2. Well, that means that in this direction, we divide by r equal to 2. So just based on that, I can kind of recreate this. 24 divided by 2 is going to get me to 12, and 12 divided by 2 is going to get me to 6, and 6 divided by 2 is going to get me to 3. So I'm able to reproduce this sequence, and from there, I can generate my formula. Right? Here it is. A sub n is equal to the initial value a times r to the power of n minus 1. Right? That's just using this formula, the general form of a geometric sequence, which is a times r to the n minus 1 power. Guarantee you the last test is going to have stuff like this, geometric sequences. Based on some limited information, find the closed formula. Use that closed formula to do something else. Maybe find the 10,000th term on this list or something like that. Right? So whenever you run into those kinds of questions, your mission is to find the value of a, the first value on the list, and the value of r, the common ratio. Okay, let's look at another example. Here's a case where the initial value is a 2, and then the next value is a negative 10, and then a 5, and then a negative 150. Okay, so you can grab any two consecutive numbers and divide them to get your common ratio. So 50 divided by negative 10 gets you to negative 5. Right? 50 divided by negative 10 gets you to negative 5. Or any other common value, negative 250 divided by 50 is equal to negative 5. Good. Make sure that they're consecutive on the list, though, in order for this to work out so easily. That won't always be the case. Sometimes you might only be given, say, the number negative 10 and the number 1250, so you won't be able to just divide them quite so easily. But we'll look at an example like that in a little bit so you can see what to do in a case like that. Good. So we can find the common ratio. In this case, it's negative 5, and the initial value was 2. So then it's just a real simple, direct substitution, again, using our general form for a geometric sequence. Right. So here is the 2 is the a, and the negative 5 was the r. Okay, here's another example. Here's a sequence, 1, comma, 1/3, 1/9, 1027, 1081. So again, if you take one term and divide it by the other, okay, so let's take 1/9 and divide it by 1/3, right? That's what we've been doing so far. We take a number and divide it by the one that came right before it. So I know they're ugly fractions, but still, let's work with those. So the way to simplify this is to leave the numerator alone, right? And then the division, we turn it into multiplication, and then we multiply it by the reciprocal of the denominator. So we get that, and now that reduces 3. So we end up with 1/3. Good. So we follow the form to find the value of r. And now we have the initial value on my list was 1, and the common ratio is 1/3. And that's how we get this form once again, using a sub n equals to a times r to the n minus 1 power. I hope. Okay, next one. Let's look at a graph. Let's see what happens when we graph them. So the graph of a geometric sequence is defined by a sub n equals to 1/5 times 2 to the n minus 1 as shown in figure 1. Note that the points on the graph lie on the graph of the exponential function, right? So what's the difference between these two? So we have a sub n is equal to 1/5 2 to the n minus 1, right? This is a geometric sequence. Geometric sequence, which means that there is a list of numbers, the first one on the list, the second one on the list, the third one on the list, right? That's what a geometric sequence is. It's going to be a list of numbers. They just happen to obey this set of instructions. The first one on the list, a sub 1, is equal to 1/5 times 2 to the 1 minus 1. 1 minus 1 is 0. The whole thing is just going to be equal to 1/5 times 2 to the 0. 2 to the 0 is 1, so the whole thing is just 1/5, right? 1/5. Okay, that's what we expected. It's the initial value a. Then a sub 2 is going to be equal to 1/5 times 2 to the power of 2 minus 1, which is going to be equal to 1/5 times 2 to the first power, or just 1/5 times 2. So that'll be 2/5. Right, that's the second one on my list, 2/5. Third one on my list. Third one on my list is going to be equal to 1/5 times 2 to the 3 minus 1, which is equal to 1/5 times 2 to the second power, which will be 4/5. That's the third one on my list. Good. Okay, well, I could see that the common value r, but the common ratio r is 2. So at this point, it might just be easier to think about it as just multiplying by 2 every time instead of plugging it into the formula and doing this. Which is fine, either way. So I can easily tell that the next one on my list is just going to be to multiply this one by 2 to get me to 8/5, right? And then the next one's going to be 16/5, and then the next one's going to be 32/5, and so on and so forth, right? Good. Okay, well, what is... So a sub 1 is the first one on my list. A sub 2 is the second one on my list. A sub 3 is the third one on my list. What is a sub 0.2? Well, that doesn't make any sense, right? I mean, I could plug it in. I can go through the process of saying, let's put a 1/5 here, and let's put a 0.2 there, and a minus 1 there. So I can mathematically get an answer. True, negative 0.8. So this has a math answer, right? Some decimal. But what does it mean in terms of this? This is the first number on my list, the second number on my list. What is the 0.2 number on my list, right? So we don't want to have that. That just doesn't make sense within the context of the definition of what this means. Right? This is a list of numbers where n is a location. So n has to be a counting number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. However, this does have an actual answer. I can plug it in and get a decimal. It just doesn't make sense in the context of this. However, if we then instead think about something very closely related, which is a function that looks almost the same, what if we just had, let's put it in green, consider the continuous function. Y equals to 1/5 2 to the power of n minus 1, right? Or if you want to write it in a different way, we can also rewrite this as f of x equals to 1/5 2 to the power of x minus 1. So we've completely stripped away the concept of this as a list of numbers. Now we just have a continuous function, right? We get to plug in anything we want for x, right? Any number goes into here. It's the domain of x, right? Here's the input. And there isn't any mathematical reason for why we should limit the input. We're not going to end up dividing by 0 in any way. We're not going to end up taking the even root of a negative number. So the input seems like it's all real numbers. Good. And then we plug it in into here, and then out will come out the output, right? Which, well, if we think about this is an exponential function. So the output of an exponential function is not going to be all real numbers. In this case, it's going to be all positive numbers, not including 0. Good. We can manipulate this a little bit. play around with this thing a little bit. This is f of x equals to 1/5 2 to the x minus 1. So then this thing can be rewritten as f of x equals to 1/5 2 to the power of x times 2 to the power of -1, right? Because when we have two exponential numbers with the same base, we add the exponents. So if we added the exponents, we would have this. You can rethink of x minus 1 as x plus -1. Good. Okay, well then this can be rewritten as f of x equals to 1/5 times 1/2 times 2 to the x power, just rewriting the 2 to the -1 power as 1/2. So the whole thing is f of x equals to 1/10 times 2 to the x power. Good. Well, then that's just an exponential function with base 2 and some constant 1/10 in front of it. Good. So if you remember the graphs of exponential functions, you would remember that an exponential function that has a base that's bigger than 1 will have a general shape, a general form that looks like this. The graph of any exponential function that has a base bigger than 1 has a shape that looks like this, right? The bigger the x goes, as x goes toward infinity, as x heads that way, heads toward positive infinity, the function f of x will also go up toward infinity, positive infinity, right? As x goes toward negative infinity, then the function f of x heads toward 0. And that looks weird. I have up for infinity, so I guess maybe I should point down towards 0. This thing goes towards 0. Right? It never actually crosses the 0. It's never actually going to be equal to 0. There's no input value of x that gives you a 0, or a negative number. There's no input value of x that's ever going to give you a negative. Good? Okay, so what's the relationship between these two? Well, this is a sequence of values that that's only valid for specific values of n. So when n is 1, we'll have a sub 1. That'll be a dot on this function. When a is 2, then this will be a particular dot there, and then that guy will be a sub 2. Right? When a is 3, x is 3, it'll be a particular value on that function, a sub 3. Sort of, kind of, maybe? Let's graph it with Desmos. It's bound to be better than mine graphs. Let's get rid of all of these things. Okay, so let's begin with a table of values where we had, say, n, and we had the equation was, I forgot, was it 1/5? So I'm going to push this one into there. It was 1 divided by 5, and then 2 to the power of n minus 1. Okay. So the first one on my list, oops, n minus 1 is up in the exponent. No, wait. Get in there. Minus 1. There we go. Okay, so 1 leads to 0.2, and then 2 is going to lead to 0.4. That's what this is. And then 3 is going to lead to 0.8. That's what this is. Okay, and so on and so forth. All right, so let's put that over here. Now let's graph the function version of this. So what if we had y equals to 1/5, 1 divided by 5, and then 2 to the power of x minus 1, like that. Okay, so here is the function version of this, and I can make it f of x as a function. So here, it's the domain is all real numbers. So when we graph it, the domain is all real numbers, and the output is all positive real numbers. Good. I manipulated a little bit, and let's just confirm that it equals the same thing. So after I manipulated this a little bit, I said it was equivalent to 1 divided by 10, 2 to the power of x. 2 to the power of x. Oh, why does it have an h in there? Right, so see, they both give you the exact same graph, right? So it's just a graphical confirmation that the black one, which is this function, looks identical to the red one, which is this function, right? So that helps me feel a little bit more secure that my algebraic manipulation worked, that this one really is equal to that one. They have the same solution sets, they have the same graphs. Okay, so you can graph either one of these. So here is the continuous case, and now if we graph the geometric sequence part of it, we see that these guys are just individual dots on that curvature. Okay, let's try a couple more. How about n equals to 4, n equals to 5, n equals to 6. Let's put them in red. Maybe they pop out a little bit more. Good. I think actually there's a projector mode. That'll make it better. There we go. Any questions about that? It's a very subtle difference, but I think it's something to really pay attention to when you get to something related to this in calculus. It'll be important to really have the distinction in mind. The difference between an equation that's a sequence, the input values are all counting numbers, n equals to 1, n equals to 2, n equals to 3, right? And they represent a location on a list, right? But that's very closely related to its function, where the function, the domain is all real numbers, and then the sequence just happens to be individual instances of the continuous function. Any questions about that? So that's what the author is attempting to point out here. So the graph of the geometric sequence defined by this equation is given by these little dots here, right? And so notice that the points on the graph lie on the graph of the exponential function 1/5 times 2 to the x minus 1, the continuous function. Good. And so the continuous function, if we think about that one, that's an exponential function which we studied in the past, and we know that whenever the value here, r in our case, whenever that value is bigger than 1, the graph is going to grow in this direction, and whenever r is between 0 and 1, it comes down in the other direction. Right? It decreases. Let's confirm that over here again. So just the general form of any exponential function, if we have, I don't know, h of x equals to b to the x power, where b is a slider, and let's make b range from 0 through 10 by 0.1. Okay, so b to the x power. So when b is 1, well, we just have 1 to the x power, and we have a horizontal line. That one's boring. But as it gets bigger than that, then we end up with this shape. Let me zoom out. Whoa, did not go too much. Good. So when the base is bigger than 1, right, strictly bigger than 1, then we always have this sort of a shape. Here we have 4.7 to the x power, 6 to the x power, 7.2 to the x power, right? And when that base value is equal to 1 exactly, then we have a horizontal line. And when the the base value b is between 0 and 1, then it goes in the other direction. It goes like that. So when that base value is between 0 and 1, it'll have this sort of shape. As x goes toward infinity, the function gets smaller and smaller and smaller and heads towards 0. As x grows toward negative infinity, the outputs will grow toward positive infinity. The opposite of over here. In this direction, when the base value is bigger than 1, as x grows toward infinity, the function outputs grow toward positive infinity. And as x grows toward negative infinity, the function outputs get closer and closer to 0. Questions, questions, questions? Again, we're laying the groundwork for calculus, right? That's the whole point of this course, to prepare everyone for calculus. So even though right now it just seems like it doesn't make a huge difference for the purposes of what we're doing, it'll be really important when you get to calculus to already have some of this framework in place. A lot of what you do in calculus is think about what happens to a function as something goes toward infinity or gets infinitely close to something. So a lot of it is kind of picturing it and thinking about the graphs, and hopefully this helps. And also this very subtle difference between the continuous function being a smooth continuous curve, and then a sequence being a subset of those outputs, right? Individual little dots on that curvature. Good? Good, good, good. Okay, we can find the nth term of a geometric sequence if we know any two terms, as the next example shows. So let's say, for example, we're given this one, Find the common ratio, the first term, the nth term, and the eighth term of the geometric sequence. This one is super easy. It's a good one to practice on, but I would not give you something like this on the next test. It's just way too easy, right? Because, well, obviously, here is A. Good. And remember that in order to find the nth one, we just have to follow our general formula. And our general formula is a sub n equals to a times r to the n minus 1 power. So we just have to find a, and we have to find r, and a is just right there. A is 5. So we're already halfway there. And remember that r is found by dividing any two consecutive terms on a geometric sequence. So I can just take the easiest one. Why not? 15 divided by 5 equals to 3. Or I could have also said r equals to 45 divided by 15. That's also equal to 3. So I found my formula. A sub n equals to 5 times 3 to the power of n minus 1. Super duper easy. But we'll use this to build onto something more interesting. So we found the first term. Yep. So the answer, what's the first term? This part. Find the first term. Find the common ratio. Okay, the common ratio was here, r. The nth term, okay, that's that guy. We answered that. And the eighth term. Okay, so now we have to find a sub 8. That's equal to 5 times 3 to the power of 8 minus 1. Which will be 5 times 3 to the power of 7. And that's what I need a calculator. I don't know what 3 to the 7th power is. Where's my calculator? To the power of 7, 2,187, and I multiply that times 5, I'll get 10,935. Good. And well, you know, since it's only the eighth term, we could have just as easily found it by just multiplying these things. We have the third term, we have the fourth term, then we have the fifth term, then we have the sixth term, then we have the seventh term, finally we get to the eighth term. And since the common ratio is just 3, we multiply this by 3, multiply it by 3, multiply it by 3. Then we can just continue with that pattern as well, and it wouldn't be that bad in this case. 135 times 3, the next one is 405. Multiply that by 3, the next one is 1215. Multiply that by 3, the next one is 3645. Multiply that by 3, and the next one is exactly what we got, 10,935. So we could have gone this route, and it wouldn't have been that bad since we only had to find a couple. But it's important to be able to do it both ways because they could have just as easily asked you a very large number, right, way over there. Find the 113th number on my list. Well, it would take forever to multiply by 3 every time. Whereas having this nice little formula, I can just plug it right in. Right? That's the beauty, the power of having a nice closed formula. Times 3 to the power of 113 minus 1, which is equal to 5 times 3 to the power of 112. Now, not only is it a lot easier to plug it in, but also we can express an answer in its exact form when we might not be able to actually multiply it, because this is such a huge number that I bet most calculators can't actually do it, right? Let me try. 3 to the power of 112. Well, okay, it does give you an approximation, but I'm getting times 5. I'm getting 1.36 equals to 1.3694 times 10 to the power of 54. That's a huge number, right? This is 1, 2, 3, 4. 50 zeros behind it, right? That's a lot. That's a huge number. So very quickly, if I went past that, you know, the 5,000th number, the 10,000th number, at some point, we'll get to a number that's so big that your calculator can't even really give you an approximation, and it'll just say an error. But we can at least write it down if you know the closed formula. Okay, any questions? No? No questions, no questions, no questions, no questions. Moving on. Okay, let's see what the author did. Good, okay, so we take any two, 45 divided by 15, that's how we got the common ratio of 3. Clearly the initial value 5 is a. From there we can get our closed formula. And from there we can plug it into the formula to find the 8th value on my list, which is exactly the work we did. Good. Partial sums of geometric sequences. So remember that partial sums were defined as a new sequence where s sub 1 equals to a1, s sub 2 equals to, so given some sequence, a1, a2, a3, a4, dot, 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 then a new sequence is described in the following way. a1 equals to, s1 equals to a1, s2, the second one on this new list, is equal to a1 plus a2, s3 is equal to a1 plus a2 plus a3, right? The sum of the first three. And so in general, if we keep going, then we say that s sub n is equal to the sum of the first n of them. Dot, 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 keep going, and we get to n, right? The first n of them. Good? Good, good, good. Okay, so that was a sequence of partial sums. It's going to be this brand new sequence. The first one on my list, the second one on my list, the third one on my list, the fourth one on my list, dot, 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 all the way out to the nth one on my list. So it's a new list of numbers where the order matters, the first one, the second one, the third one on my list, and where they happen to be defined in this way. There is an underlying sequence where this sequence is created in this manner. Good. Okay, so we're going to look at this sequence of partial sums when we are basing it off a geometric sequence. So here is a geometric sequence, right? The first term is a, the second term is ar, the next term is ar squared, right? This is a geometric sequence. And we want to discover what is a sub n, right? What is a formula for the sum of the first n of them, right? We can express that this way. It's the sum as k goes from 1 to n of this, which is the closed formula of a geometric. We could have also said s sub n equals to this, the Riemann sum, as k goes from 1 to n of a sub k, right? Which means that s sub n equals to a1 plus a2 plus a3 plus dot, 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 and we don't stop until we get to n, right? This indicates the stopping point. And if it's a geometric sequence, then we know that a sub 1 is just a, plus a sub 2, following the form of a geometric sequence, is going to be a times r. The third one on my list is a times r squared, dot, 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 dot. All the way out to the last one on my list. And so the last one on my list is going to be a r to the n minus 1. Sorry that my r's and my n's look so similar. Good. And so this is how we can also go back to a Riemann sum involving this formula. This is equal to the Riemann sum as k goes from 1 to n of a r to the k minus 1 power. Right? This will also generate this list here. Good. Good, 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 good. Okay, so we want to find this sum. And to find this sum, somebody very, very clever came up with this idea. We want to know this sum right here, s sub n, right? What is that sum? Okay, well, it's the sum of all of these things. Okay, well, somebody thought, well, why don't we multiply both sides of this equal sign by r? So that's what this down here represents. Let's multiply the left-hand side by r, so we'll end up with r times s of n. And if we multiply the right-hand side by r, we end up with a times r, which is going to be this first term. And then if we multiply by r, we get ar squared, right? So each one of these terms gets an extra power of r when we multiply both sides by r. And that's where this comes in. Looking at the last one, the original formula had ar to the n minus 1, but if we multiply by one more copy of r, we'll end up with just ar to the nth power. Good? Good, good, good. Okay, so now we have this sequence, which is just s of n, and we have this sequence, which is r s of n. So now if we subtract them in this order, s of n minus r s of n, then I'm going to subtract them on the left-hand side in this order. And so I'll take all of these minus all of these, and a lot of them will cancel, sort of pair by pair. Here, let me expand that this way. So this is saying if I take this whole set, which is going to be a plus ar squared plus dot, 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 all the rest, right? And the last one is a r to the n minus 1 power. So I take all of those, and from those I subtract minus all of these. Well, then that's ar plus ar squared plus dot 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 dot. And the last one is ar to the nth power. Okay, so if I subtract them, then there's a lot of cancellations that are going to happen. This first term here is going to cancel with that one, right? This one cancels with that this one. Good. And then the next term, let's put it in brown, this ar squared there cancels with that one, right? When I distribute this minus, I'll get a cancellation so that this one cancels with this one. And then a little domino effect will happen. The rest will cancel. This will cancel with that one, this one will cancel with that one, right? A whole bunch of stuff will cancel. This will cancel with that, and this will cancel with that, and a bunch of stuff will cancel, 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 cancel. And the only thing that will survive all of this cancellation is going to be two things. This first term never cancels, so it survives. Here it is. And then the very last term survives. Nothing cancels with that one. So here it is. Good. So after all that cancellation, we end up with this statement. S sub n, the thing we wanted to find, minus r times s of n equals to a minus a r to the nth power. Good? Good, good, good. So rewriting it here, s sub n minus r s sub n equals to a minus a r to the nth power. And I'm just taking that and putting it right over here. Now if we factor out the s sub n, we end up with s of n, 1 minus r, equals to a times 1 minus r to the nth power, if we factor out that a. And then if we divide both sides by this, 1 minus r, we get to our final solution, which is this guy right here. This is a formula for the sum of the first n terms of a geometric sequence, as long as r does not equal to 1, right? Because if r equals to 1, then we're going to be accidentally dividing by 0, and we know that's not allowed. Good? Questions, questions, questions? So you are not expected to reproduce this. So if you're a little bit concerned about this messy stuff, don't worry about that. I wouldn't ask you to prove or to discover the formula for s of n on your own. My hope is that you were able to follow the logic through this, so it doesn't seem like a weird formula and you have no idea where it came from. Hopefully it seems like a reasonable place where this formula comes from, and now you get to use it, right? So we have a nice little blue box thing that's in your book, right? Anything in the blue box means that you get to use it. It's a given identity or theorem or something. So in this case, it's the partial sums of a geometric sequence. The formula for the partial sums of a geometric sequence, s sub n, is equal to a times 1 minus r to the nth power divided by 1 minus r. Any questions? Maybe. Okay, so let's take a look at this example. Find the following partial sum of a geometric sequence. Okay, so find the partial sum. So these little dots mean that there was a pattern established, and it keeps going in that pattern until it achieves this. So one common mistake is that people just add these four numbers, and they think that's the answer. That's not quite it. There's sort of this pattern that's established in the middle that we have to take into account. Okay, so find the following partial sums. The first thing we have to do is notice that they told us it was a geometric sequence, so that's very powerful. It means that the underlying sequence of values is geometric. So if we think about the sequence 1, comma, not plus, but 1, comma 4, comma 16, comma, dot, 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 and somewhere down the line we have 4096. This is a geometric sequence. Good. And then we're going to do partial sums by looking at this. But okay, so in this sequence, because it's geometric, it must mean that it follows this form. A sub n equals to a times r to the n minus 1 power. Well, 1 is a, right? It's the first term. That's easy. And then to get the common ratio r, all we have to do is take one number and divide it by the one that came right before it. So 4 divided by 1, that's just going to be 4. And then 16 divided by 4, that's just going to be 4. So either way, we get that r equals to 4, which was pretty easy to see if we just paid attention here. The way we go from there to there, we multiply by 4. Right? And the way we go from there to there, we multiply that by 4. So forth, and so forth, so forth, so forth. Okay, so that means that so far we've already got together the general form. A sub n is equal to 1 times 4 to the power of n minus 1. And I guess we don't really need that 1. It's just kind of messy. So we can just rewrite it as a sub n equals to 4 to the power of n minus 1. Good. Okay, the next thing I need to know is to figure out where is this number on my list, right? This one is a sub 1. This one is a sub 2. This one is a sub 3. But what is this one? A sub what? I need the value of n that belongs there so that I know how many terms am I adding to get to that number right there. Good. I don't know, it's an unknown, so I can put a little question mark. Or, since I do have some awesome algebra skills, I can let it be some unknown variable. About, I don't know, about x. Very unimaginative. I don't know. About alpha. I don't know. That looks ugly because it's a and it's an alpha, so that looks ugly. About w. All right, let's do w. Okay, so now I'm going to use this formula and find w. Find w such that a sub w equals to 4 to the w minus 1 power. And we know that in this case, that w, this thing is 4096. So find w such that 4096 equals to 4 to the power of w minus 1. Okay, so how can we solve this? Well, we take advantage of our awesome log properties, right? So let's apply ln to this side. 4096 equals to ln of 4 to the power of w minus 1. Right? One of the great reasons why we study logs is because it has a fantastic property that we get to move the exponent out in front like a linear factor, and that's how we are able to solve things that are up in exponents. So then we can rewrite that as w minus 1 parentheses times ln of 4 equals to ln of 4096. You could have also applied log base 4 to both sides. Some people would have preferred that, and then that makes the right-hand side super simple. Either way, you get the same answer. Divide both sides by ln of 4, so we end up with ln of 4096 divided by ln of 4 equals to w minus 1. And so from there, we get that w must be equal to ln of 4096 divided by ln of 4 plus 1. Good. Now I just punch that into my calculator and we get our answer. So let's see. Let's use a calculator from here. Okay, so quit that, clear, and I want to do ln of 4096 divided by ln of 4, close parentheses, enter. I get a 6 plus 1, I get a 7. Okay. So this guy is 7. Oh, so that's actually not very far down the list at all, right? Since we already had the first few numbers. We already had the first 3. It turns out that this one's the 7th one. And since I'm just multiplying by 4, it would have been pretty easy for me to just find the rest of them that way. So that's another thing you could have done. So the other way you could have found this, in this particular case, since it's such an easy question, is to do this, 1, and then the next one comes by multiplying by 4, you get to 4. Next, you get to the next one by multiplying it by 4, so you get to 16. And then by multiplying it by 4, you get to 64. And then pretty quickly, I'm going to use my calculator. So then 64 times 4 gets you to 256. Let's keep track of the location numbers. We have 1, we have 2, we have 3, we have 4, we have 5. Then multiply that by 4. We have the 6th number, which is going to be equal to 1024. And then finally, we multiply that by 4, and we get to 4096. And that's how we get to the 7th value, right? So it's the 7th one on my list. A sub 7 equals to 4096. Everyone's good with me so far? Any questions? Questions? No? Okay, well, why did I do all of this work? Remember, let's go back to this thing then. So this is a partial sum of the first n numbers. And now that I know that in this case n equals to 7, then I'm saying that this is a partial sum of the first 7 numbers. Good. So now we're looking at this. Let's squeeze it over here. We have s sub 7 is equal to the sum of the first 7 numbers. Sum of first 7 numbers. Good. So s sub 7 is exactly what they wanted. 1 plus 4 plus 16 plus ... plus 4096. Now again, in this case, it's such an easy little question that we could just add these numbers. It wouldn't be that hard to get my calculator and just add these. That's going to be 5, 21, 85, right? So just add these, no big deal. But we want to use our formula because very quickly we're going to take this simple little problem and blow it up so that you really can't do it by any other method but following the formulas that we have, right? Okay, so we have a formula that says that in general, if we're adding the first n numbers, then the formula says that it's going to be a times 1 minus r to the nth power over 1 minus r. Right, that's just from this little formula over here. S sub n equals to a to the power of 1 minus r to the nth all over 1 over r. Okay, so we just plug them in based on the numbers we have. So we want to know 7, the sum of the first 7 numbers, where the first initial value is a 1, a was a 1, and then r was a 4, so we get 1 minus 4 to the power of 7 all over 1 minus 4. Good. So the denominator is going to be a negative 3, and the numerator is going to be some negative number, right? A large negative number divided by negative 3. So the whole thing is going to be the value we expect, a positive answer. So this is going to be 4 to the 7th power, 4 to the power of 7, and then 1 minus that. So this is 1 minus 16,384 divided by negative 3. Good. Here. So s of 7 is equal to 1 minus that answer, gets you to negative 16. Oops. Come on. Negative 16,383 divided by negative 3. So that's going to get me to s of 7 equals to 5,461. Good. Good. Any questions? Let's see if I can zoom all out and get it all in one thing. Okay, so we discovered that the sum of these terms, it turns out that there were 7 of them. So part of the process of finding this answer is to take advantage of the fact that we know it's a geometric sequence to find the formula, the closed formula for the underlying geometric sequence. From that, we were able to deduce that this number must be the 7th one on the list. That's important for our formula because we need to know n, the value of n, meaning how many numbers are we adding from the underlying geometric sequence. Good. So the sum of all of these numbers is this number, 5,461. Any questions? No questions, no questions, no questions. Good, easy, sort of, kind of. Okay, so let's see what the author did. Probably something very similar. So here is the sequence, noting that a is 1, the common ratio is 4, and then from that you can get the closed formula, 4 to the n minus 1, then 4 to the 6th power equals to 96, so that's how we were able to figure out that the n is equal to 7. Plug it into this formula and you get the same answer, 5461. Questions, 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 questions? Okay, one final concept in this section and we'll take our break. So we're looking at the sum of the first n values, right? That's what we've been looking at, s sub n. So s sub n can be expressed this way. So we've been looking at cases where we had S sub 1 is equal to A1, and then S2, the first sum of the first two is S1 plus A1 plus A2, right? S sub 3 is equal to A1 plus A2 plus A3, right? Remember that in Riemann sum notation, this can be expressed as this. K goes from 1 to 3 of A sub K, right? This gives you the sum of A1, A2, A3, which is this. We would never, well, we probably would stay away from expressing it this way when it's so easy to express it this way, right? But then in general, as we keep going, we see that if we want to find the sum of the first n of them, we get that this is A1, A2, A3, dot, 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 and then we don't stop until we get to the nth one. Okay. And so we can express this as the sum of this goes from 1 to n of A sub n. Okay, but now we want to think about, well, what happens if we keep going past that? What happens as we go toward infinity? Okay. All right, well, we saw that the sum of the first n of them, S sub n, is equal to A times 1 minus r to the nth power all over 1 minus r. Right? That's the formula for the sum of the first n values of a geometric sequence. So as n gets larger and larger, we are adding more and more of the terms in this series, right? More and more of these terms in this series. We're adding up eventually an infinite number of values from the underlying geometric sequence. Good. And so intuitively, the sum will get larger and larger and larger, assuming all the terms we're adding are positives. Then the sum will be getting larger and larger and larger. So intuitively, as n gets larger, S of n gets closer to the sum of the entire series. Right? So if I wanted to add all of them up, A1, A2, A3, all of them, all the way out to infinity, well, whatever that number is, that sort of that, kind of keep in your head what that number is, well, as these partial sums get larger and larger and larger, they will get closer and closer and closer to the actual sum of all of them. Does that make sense? So here, this is what I'm trying to say. If we have A1 plus A2 plus A3 plus A3 plus dot, 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 forever. Okay, so if I want to add these up forever as n goes toward infinity, all of them, well then one good guess is to pick a large value of n. Find the sum of the first 87 numbers. That's a pretty good guess. Like, oh, that's not good enough. Okay, well then find the sum of the first 830 of them. That's a pretty good guess. Well, not good enough. Find the sum of the first 10,937 numbers. Pretty good guess. Not good enough. But as this number gets larger and larger and larger, eventually this this value will get closer and closer to the sum of all of them. Good. 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 Okay. Now, if r is okay, so now notice that as n gets larger, 1/2 to the power of n gets closer and closer to 0. Right? If we have 1/2 raised to the power of n, it gets closer and closer to 0. Thus S of n gets closer and closer to 1 minus 0 when 1 minus 0 gets closer and closer to 1. So if this number here, if r is a decimal value between 0 and 1, I don't know, say 1/2, for example, and we take r to the power of n, then maybe like 1/2 to the power of n. So as these powers, as these exponents get larger and larger and larger and larger, then this will get closer and closer and closer to 0, right? As long as that r value is a value between -1 and 0. Right? This is all connected to an exponential number. If we had 1/2 to the power of n as a function, remember that if this base number is between 0 and 1, then the graph of a continuous one looks like this. Let's make this a continuous function. A continuous function looks like this. So as the inputs get larger and larger and larger and larger, then this thing gets closer and closer to 0. Right? On the other hand, if we had a function g of x equals to, say, 3 to the power of x, When this base number is bigger than 1, remember that its exponential function will have the other shape. It'll go in this direction. So as x goes toward infinity, this blows up out of control and goes toward infinity. Good. So exploring this formula here, whenever r is bigger than 1, this is going to get really, really, really big. And then the whole sum is just going to go toward infinity. Positive or negative infinity, depending on, well, let's say r is a positive number bigger than 1. So this has got to be a positive, a really big positive number. And then 1 minus this becomes a negative. So the whole thing is going to become one big positive number. Good. And it just blows up and goes toward infinity. On the other hand, if r is a value between 0 and 1, then as r is raised to the power of n and n goes toward infinity, this will converge toward 0. It'll get closer and closer and closer to 0. So in a situation like that, this thing can be simplified. Okay? So if r was a value between 0 and 1, say a half, just out of just kind of randomly choosing a number between 0 and 1. So then as n gets larger and larger, that whole thing gets closer to 0. So therefore, 1 minus r to the power of n will get closer and closer and closer, right, as n approaches infinity. Then this gets closer and closer. Oh, and I'll also put that r is a value between 0 and 1. Then this gets closer to 1 minus 0. Right? This is approaching 0, which means the whole thing is getting closer and closer to positive 1. Good. And so we arrive at the point that if r is between 0 and 1, then as n gets larger and larger and larger and larger, then s sub n, which was the formula of a times 1 minus r to the n over 1 minus r, this part of it goes towards 0. This goes towards 0. So we just end up with this thing approaches a over 1 minus r. Good. So we have a formula for the infinite sum of a geometric sequence. Sort of. It's a lot to take in, I think. I'm not sure if I did a great job, but any questions? Did any of it make sense? So the notation we like to use is that s sub n means that we're adding up the first n numbers in our list. But if we drop the n and just say s, s represents the sum of all of them, all the numbers in the original sequence. So as n gets larger and larger and larger, we say that the infinite series converges or is convergent if it goes toward a particular answer, if the answer exists. And it will exist as long as r is a value between 0 and 1. Okay? The number s is called the sum of the infinite series. And if that infinite series does not converge to something, it just blows up and goes toward infinity, then we say that the series diverges. Does that make sense? Maybe. Sort of, kind of. Okay, so if we have a geometric sequence in particular, here it is, and we want to find the sum of the first n numbers, the first 3 numbers, the first 7 numbers, the first 20 numbers, doesn't matter. As long as we have a fixed number of values that we want to add, then here is the closed formula for that. Good. However, now, what if you want to add all of them? I don't want to add the first 20 numbers. I want to add all of them out to infinity. What is that going to be? Well, if these individual numbers are just getting bigger and bigger and bigger and bigger and bigger and bigger, then it makes sense that if we add all of them, they're just going to blow up toward infinity. Okay? So here is an example. Let's say I have 3, and then I'm just adding them, say I'm multiplying them by 2. So we get 3, then we get 6, then we get 12, then we get 24, then we get 48. Right? Here is a geometric sequence. It's a geometric sequence where a is 3 and r is 2. Good. So I can find s sub 10, the sum of the first 10 of them. That's easy. That's going to be equal to 3, which is the a, times 1 minus the 2, which is that common ratio, to the power of 10, divided by 1 minus 2, the common ratio. Good. So now if I punch that into my calculator, 2 to the power of 10, 2 to the power of 10 is 1024. So this will be equal to 3 times 1 minus 1024 divided by -1. So S sub 10 is going to be equal to 3 times, not negative, 3 times 1023. Okay. 1 minus, well, here, just to make sure. I'm getting a negative in the numerator and the negative in the denominator. Right? So this will be negative 1023 divided by negative 1, which gives me that S sub 10 is equal to 3 times that. So 33069. If I add the first 10 numbers in this list, I'm going to get 3069, right? And this formula works for any closed numbers, right? I can say, let's find the first 119 of them, add them all up. What is that? Okay, we'll just plug it into this formula and we'll get an answer. But what we're interested now in is what happens is I add all of them, not the first 10, not the first 119, all of them. The sum of all of them is just S with no little subscript. It's just the sum of all of them. Well, that's going to be 3 plus 6 plus 12 plus 24 plus 48 plus ... for infinity, right? Forever. Well, if you notice, every individual number keeps getting bigger on its own, and I want to add them up forever. It makes sense that this is just going to be an infinitely large number, right? This isn't going to converge to some pretty little number. This is just going to keep growing and growing and growing and growing, right? So there is no finite answer. The answer is just it keeps growing forever. Okay. Okay. On the other hand, if we happen to have a sequence, and notice that means that R is 2, R is bigger than 1, R is bigger than 1, then that means that this just goes out to infinity, right? It diverges. We say it diverges because it doesn't go toward any particular value. Good. Diverges. Sum diverges. Good. On the other hand, if we have another geometric sequence, a geosequence, say A equals to 3, but this time R equals to, say, R equals to 1/5. Okay, so here's my list. It's going to be equal to 3, and then the next number is going to be 3 divided by 5, right, multiplied by 1/5. Then the next number is going to be 3 divided by 25, right, and then the next number is going to be 3 divided by 125, and then the next, right, so here's my list of numbers. So now I can apply the same reasoning to find the first 10 numbers. That's going to be equal to 3 times 1 minus 1/5 to the power of 10 divided by 1 minus 1/5. Good. Good, good, good. Notice that in this case, R is between 0 and 1, and a couple of things happen. This is going to be a very, very small number, right? 1/5 to the power of 10 is a very small decimal. 1 minus that is going to be a positive answer, and 1 minus 1/5 is going to be a positive answer. So in the previous case, we ended up with a minus over a minus, a negative over a negative. Here we'll end up with a positive over a positive. But this will give us the answer we want. So let's just plug it into our calculator. S sub 10 is going to be 3 times, the denominator is just going to be equal to 0.8. 1 minus 1/5 is 4/5, which is 0.8. And then 1 divided by 5 to the power of 10 is a huge number. 1 minus that equals another huge number. Just using my calculator, I'm getting the numerator is 0. Now, a bunch of 9s here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 6 9s. 1, 2, 3, 4, 5, 6. 8, 9, 7, 6. That's what I'm getting. So I want to take that thing divided by 0.8 and then multiply that by 3. And I'm getting 3.7974. I'm getting S sub 10 equals to 3.74999, something like that. So pretty close to 3.75. Any questions about this? We're given this geometric sequence where A is 3 and R is 1/5. Here it is, the first few numbers. And if I want to find the sum of the first 10 numbers, I use this formula, and I get that it's approximately 3.75. Good? But what if I want to add them all? S, right? No subscript. That's the sum of all of them. That means I want to add 3, and then I want to add 3/5, and then I want to add 3 over 25, and then I want to add 3 over 125, and so on and so forth, forever, as this goes to infinity. Well, this is different from the previous one. It's a very important distinction to point out here. Up here, when we were working with this one, when R was 2, each individual number was getting bigger and bigger and bigger and bigger and bigger. So if you're adding an infinite sequence of values, and each individual number is getting bigger, then the sum of all of them has no chance of ever adding up to a constant. It's just going to blow up toward infinity. Good. But on the other hand, in a case like this one, where the r value is between 0 and 1, that means that each individual term is getting smaller and smaller and smaller and smaller and smaller at a very fast pace, so that even though you're going to be adding an infinite number of values, because each number is getting really close, right, really close to 0, then this stands a chance that even though I add them forever, they add up to some constant number. Good. And that's when we use this formula. This is the formula for the infinite sum of a geometric sequence. Good. And this formula only works as long as r is a value between 0 and 1, like it is in our case right here. Okay, so now if I want to find this infinite sum s, the formula is just to do a over 1 minus r. A in our case was a 3, divided by 1 minus r, which was 1/5. This is going to be 3 divided by 0.8. And 3 divided by 0.8 gets you to 3.75. Which is, this thing goes to 0 so quickly that even adding the first 10 of them got me pretty close to that, right? But now this confirms that no matter how far out you go out 100 places, you go out 300 places on the list, you add them all up, you're going to get really close to this number. It doesn't go out to infinity, it goes out toward this number. Good. So we say that this is a case where the sequence converges. Questions? No? No? Okay, let's get back to this thing over here. Almost done. We'll take a break in a bit. So it follows that, okay, so S of n as n goes toward infinity approaches this. So here is the formula for the sum of the infinite geometric series. Okay, so notice they snuck in the word series in here. We've been working with sequences. A sequence is a list of numbers. But now if we want to add up that list forever, that infinite list of numbers, and we want to add them all up, now that's what we call a series. Okay, so here is the formula. This is a formula for a geometric sequence, but if we want to add them all up to infinity, right, starting at 1, going out to infinity, so if we add these all up forever, then that is a geometric series. Good. And that series will converge, it will have an answer as long as the r value, the absolute value of the r, is less than 1. Good. And it will add up to this amount. It will converge to this. On the other hand, if the absolute value of r is greater than 1, then the series diverges. Right? It just blows up. It will not get infinitely close to a specific number. That's what that means. Questions? Sort of, maybe, kind of. Okay, so here's a couple of examples. Determine whether the infinite geometric series converges or diverges, and if it converges, find the sum. Okay, so part A, let's look at this one. Is that going to converge or diverge? So let's look at the underlying sequence, right? The geometric sequence. Sequence means it's just the list of numbers without the sum part of it. Okay, so we got the number 2 was the first value, then 2/5, then 2 over 25, then 2 over 125. That looks familiar. Okay, so the first value on my list, A, is going to be a 2. And then to find the common ratio, all I have to do is take any number and divide it by the one that came right before it. So let's do 2 over 25 divided by the one that came right before it is 2 over 5. Multiplying the numerator times the reciprocal of the denominator, we get that. These cancel, these reduce. We end up with 1/5. Okay, so the common ratio is 1/5. A is equal to 2. Note that because this is a geometric series with absolute value of r, which is absolute value of 1/5, being less than 1, it converges. So we have that 2 plus 2/5 plus 2 over 25 plus ... forever. for infinity here. Just goes on forever. That is going to be equal to s, where s is equal to a over 1 minus r. Good. So s, the sum of all of these forever, is equal to a, which was a 2, divided by 1 minus 1/5. Good. So s is equal to 2 divided by 0.8. 2 divided by 0.8, I get a 2.5. 2.5. Good. So the sum of all of these values forever, they're going to add up to 2.5. Good. Kind of an interesting idea that if we add something forever, right, an infinite number of terms, and yet they just add up to a very small number, really. I think I mentioned before this sort of idea, if you think about the pi, when I first introduced trigonometry, we talked about this idea that if we have 1 pi, and on day 1 you eat half your pie, right? Day 1 you eat half the pie, and then on day 2 you have this much left, so on day 2 you eat half of what you have left, and what you have left is 1/4, right? So then, so far you've eaten a half, and then you've eaten a fourth, and then on day 3, well, you have half of what you have left, so you had 1/4 left, and you eat half of it, that's going to be 1/8. So you eat that much on the next day, 1/8, and so on and so forth, right? The next day you eat half of that, and so the next day you eat 1/16, right? And then you keep going that way, dot, 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 dot. So mathematically we could see that we can come up with a long, infinite list of fractions that we're adding, right? On day 1 I ate half the pie, on day 2 I ate half the pie, right? So we can index these by counting numbers. 1, 2, 3, 4, day 1, day 2, day 3, day 4, dot, 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 dot. So there's this infinite list of fractions, and what do they all add up to? Well, they have to add up to 1, right? So I know it's an infinite list, but this infinite list has to add up to 1 because ultimately there's only 1 pi. Good. Questions? Questions? Okay, so that's what we've established here. We have this infinite list. This goes on forever. And intuitively, I think you think if you're going to add up an infinite number of numbers that they're going to be a really big answer or infinity, but they just add up to 2.5, 2.5. Good. Okay, what about this one? Here's another infinite list of numbers. Well, they tell us that they're both geometric. And what's the common ratio going to be? Well, since it's already written in this form, I can easily tell that the common ratio is going to be 7/5. Right, let me write it over here. Part B. 7/5. I started off with what? With 1? Yeah, 1. Part B is 1, and then 7/5 plus, and then 7/5 squared, plus, and then 7/5 to the 3rd power, plus, dot, 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 dot. Okay, we're told it's geometric, right? So the underlying sequence is geometric. It must follow this form, a times r to the n minus 1. And so from here, I can tell that a must be 1. And the common ratio is just 7/5, right? How do you go from here to there? Well, you multiply it by 7/5. How do you go from here to there? Well, you multiply it by 7/5. So, or you can just, if you really want to go through the trouble of dividing these, we get 7/5 to the power of 3 divided by 7/5 to the power of 2, any number divided by the one that came right before it, then this cancels with that and just gives you 7/5. Okay, so I hope it's clear that the common ratio value r equals to 7/5. Right, so this is a case where the absolute value of r is bigger than 1. This is a case where the individual terms are growing. They're getting bigger and bigger and bigger and bigger. 7/5 squared is bigger than 7/5. 7/5 to the power of 3 is bigger than 7/5 to the power of 2, right? Because this underlying value is bigger than 1. So if the individual terms are getting bigger and bigger and bigger, and you want to add these up toward infinity, then it's not going to converge to anything, right? It's going to blow up toward infinity. It's just going to grow, grow and grow and grow. So we just say that this diverges, right? The infinite sum, S diverges. Good. Any questions? Questions? So your book has a really nice graphic of the quick little example I just pointed out. And we've worked with this one before about having a pie or a cake or something. And on day number 1, you eat half. On day number 2, you eat half of what you have left, so you really eat a fourth. On day number 3, you eat 1/8. And day number 4, you eat 1/16, so on and so forth, right? So we can create this infinite sum of fractions that represent how much of the cake you've eaten as a function of the number of days. So how much have you eaten the first day? Half. How much have you eaten the first 2 days? Well, you add these two together. That's how much you ate the first 2 days. The first 3 days is the sum of these 3. The first 4 days is the sum of these 4, and so on and so forth. And so we can establish this infinite sum. And we can condense that down in Riemann notation like this, as we can see that they end up being powers of 2. Right? This is 2 to the power of 2, 1 over 2 to the power of 2, 1 over 2 to the power of 3, 1 over 2 to the power of 4, and so on and so forth. So we can rewrite it as 1 over 2 to the power of k. Okay, and we worked with this one before. If we start adding the first couple of them, a pattern emerges. If we add the first one, this is the half. If we add the first 2, get a common denominator, combine them, we get 3/4. We add the first 3, common denominator, we add them, we get 7/8. Right? We worked with these yesterday, I think. So for this particular case, we start to see a pattern, and it turns out that the pattern is that the sum of the first 4 of them is going to be 4 squared over 4 squared minus 1. Right? I'm sorry, 2 to the power of 4, not 4 squared. 2 to the power of 4, 2 to the power of 4 minus 1. 2 to the power of 3 gives you 8 minus 1, so 2 to the power of 3 minus 1. Good. And then if we simplify that, we get to this formula. So we saw that yesterday, I think, somewhere. S of n equals to 1 minus 1 over 2 to the nth power is a formula that describes for you the sum of the first n values of this particular sum. And again, as n goes to infinity, 2 to the power of n, this denominator, gets infinitely large. 1 over a number that's getting infinitely large is going to go towards 0. So as n goes toward infinity, this whole sum approaches 1, which makes sense going back to this because there's only one cake. So as the number of days goes out toward infinity, eventually you'll eat one cake. You can't stop at any particular day, though. Even if you go out to n equals to 100, the first 100 days, how much of the cake have you eaten? Well, you haven't eaten all of it yet. There will always be a tiny little sliver left, right? Because you're always eating half, 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 half. Every day you eat half. So it's this interesting math phenomenon that no matter how many days you go out, there's still some amount of cake left. But if you let those days go out to infinity, then we get to 1. Right? So 1 equals this infinite sum. If we didn't go to infinity, if we stopped anywhere, it wouldn't equal 1. It would be really close to 1. But just the fact that we're letting this go out to infinity is what makes it equal to 1. Good. Okay, so that was a nice graphic that the book has. And then, they're arriving at the same conclusion here, that the sum of this infinite geometric series is given by this formula. Now let's try one of these examples. I really love these kinds of examples. How about number 80? Let's do number 80. Express the repeating decimal as a fraction. Express the repeating decimal as a fraction. Let's do that one. This is chapter 12, section 3, number 80, and it has 2.1125 bar, and it says express the repeating decimal as a closed fraction. This is one of my favorite kinds of problems from this section, so you know it's going to make an appearance on the exam. Let's make sure you know how to do this one. Okay, so first of all, this little bar is indicating that we have a repeating decimal, right? So this is the same thing as 2.11, and then this 2.5 begins to repeat itself, right? Forever. Forever. So what we're looking for is some sort of a fraction, a closed fraction, a over b, such that when you divide them, you get this infinite decimal. Now, it's very easy to come up with an approximation. There's lots of shortcuts out there, several shortcuts out there that can arrive at it. But in order to get the exact answer, it's best to do it in the way that I'm about to do it. And the way I'm about to do it takes advantage of this being a geometric sequence, so it's a good, appropriate example for this section. My point being that if you want to get full credit on the test, you have to use this geometric formula. So the question will say something like, make sure to use the infinite geometric series formula to convert this into a closed fraction. So don't follow those other shortcuts that are admittedly easier, right? But we're not studying this to make life easy. We're doing it to have fun, of course. At any rate, okay, so how do we proceed? The first thing we have to do is separate this into two parts. The part that does not repeat and the part that begins to repeat. So this, I'm going to break it down into 2.11 plus 0.00, two spaces, right? And then the repeating part. Come on. 2, 5, 2, 5, 2, 5, 2, 5, dot, 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 dot. Okay. Now, when it terminates like this, it's really easy to turn it into a fraction. All you have to do is write the number down, divide it by 1, and then remember that if there are two spaces, then you put 2 zeros. 211 divided by 100 gives you 2.11. So that part's easy. We got that. Now, the next part. We need to come up with a way of expressing this whole thing as a fraction, simple fraction. And once I do that, then I can get common denominators and all that and come up with one simple fraction and I'll be done. Good. Okay, so in order to put that value there, to figure that out, I'm going to go off to the side and just work with this infinite decimal here. 0.0, 2 spaces, and then 2, 5, 2, 5, 2, 5, 2, 5, forever. Good. Okay, so now what I'm going to do is, again, break this up into pieces in the following way. I'm going to say that it's equal to 0.025, the first place where it begins to repeat, I'll cut it off there, plus 0.1234 spaces, and then a 2, 5, plus 0.123456 spaces, and then 2, 5, plus 0.12345678, and then another 2, 5. Okay, so you start to see the pattern that we develop here, dot, 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 dot. Eventually, if I added all of these, I would get 0 point, and then notice that the first term is 0 for all of them following this pattern, so the first term here would still be 0. And then the next term, well, the first two terms are 0 for all of them, right? The first two terms are all 0 following this pattern, so the first two terms would be 0. And then the next two terms have a 25 right here, and then there's 2 zeros below it, 2 zeros below it, 2 zeros below it, forever. So this 25 is the one that ends up being there. And then the next two 25s here, notice that there's nothing but zeros underneath them, so then they end up being here. So this is my justification for why this sum right here is equal to exactly the one we're working with, right? The next two have nothing but zeros underneath them forever, right? All these are zeros underneath it, so that's what gives me this 25. And then finally, the last one, I guess I'll just keep it in black. Following this pattern, the next one would have nothing but zeros underneath it, and so eventually they give you that one. Good. So hopefully I've convinced you that this infinite sum following this particular pattern is equal to exactly the one we want to work with. Okay, so that's the next step. So I'm going to write it this way. This is 0.0025 plus 0.1234, then 25, plus then 0.1, then 0.0, 1, 2, 3, 4, 5, 6 zeros, then a 2, 5. Okay, and then keep going that way, that pattern like that. Good. Okay, now I want to get rid of the decimals and turn it into fractions. And as long as it's a non-repeating, right, it terminates, a decimal that terminates, then converting each one of these into a fraction should be pretty easy. This is just going to be 25 divided by 1 with, and then we count how many spaces. 1, 2, 3, 4 spaces. So that would be 1, 2, 3, 4 zeros. Good. And then the next one is going to be a 25 divided by 1 with 1, 2, 3, 4, 5, 6 spaces. So 1, 2, 3, 4, 5, 6 zeros. Good. And then the next one would be a 25 divided by 1 with, and this is 1, 2, 3, 4, 5, 6, 7, 8 zeros. So 1, 2, 3, 4, 5, 6, 7, 8 zeros. Okay, we get the idea. The pattern continues that way. Okay. All right, well, let's write these in exponential notation, make things a little easier. So this one is going to be equal to this one, let's write it as 25 times 10 to the power of 1, 2, 3, 4. Okay. And then this one is 25 over 10 to the power of 1, 2, 3, 4, 5, 6. Right? Notice that that's one of the properties of powers of 10. 10 squared is 100. Right? 10 times 10 is 100. And 100 times 10, if you have 10 $100 bills, you have 1,000. 10 to the power of 3 is 1,000. Okay, so there's a nice little pattern. The number of zeros gives you the power of 10. Okay? So that's how I can easily tell that 10 to the power of 6 is 1 with 6 zeros. 1, 2, 3, 4, 5, 6. Okay, and then the next one is going to be 25 over 10 to the power of 8, and so on, forever. Good. Okay, so now we see that this is a geometric sequence where this is the first one in my series, and then to get to the next one in the geometric sequence, I multiply by the constant ratio of 1 over 10 to the power of 2. Right? You can also divide them. Is that r equals to, say, 25 over 10 to the power of 6 divided by the one that came right before it, 25 over 10 to the power of 4, like this, which means that r equals to 25 equals 25 over 10 to the power of 6 times the reciprocal of the denominator would be 10 to the power of 4 divided by 25. And now this cancels with that, and this reduces with that, so the whole thing just equals to 1 over 10 squared. Good. So that's what this is. This is a geometric series, goes on forever. I want to find that infinite series. This is a geometric series where a, the initial value, is this 25 divided by 10 to the power of 4, and r is equal to 1 over 10 squared. Good. So that means that this infinite sum is equal to s, which is given by the formula of a over 1 minus r. So s is equal to a, which is 25 over 10 to the power of 4, divided by 1 minus r, which is 1 over 10 squared. Right, so that's that, and that's this, and that's that. Right, so all we have to do is simplify that. Simplifying the denominator, this is going to be equal to 25 divided by 10 to the power of 4, divided by, the denominator is going to be equal to 100. Let's see over here. 10 to the power of 2 is 100. There's 100 over 100 if we multiply this by 100 over 100. So we end up with 100 minus 1 is 99, all over 100. Right, so this is the same thing as 99 divided by 10 to the power of 2, which is 100. Good. So now we multiply the numerator times the reciprocal of the denominator. 25 over 10 to the power of 4 equals to 10 to the power of 2 divided by 99. And then these guys cancel. This cancels with that, reduces that. And so I end up with s equals to 25 divided by 19900. Right? 100 times 99. Good. And at this point, I can confirm my solution to make sure that it works out. Let's go over here to the calculator and confirm that this is going to give me the decimal, the infinite decimal that I expect it will. Let's go here. So let's clear this. So 25 divided by 9900 equals to this. And I know the calculator cuts it off, but it's going on forever. Right? This will go on forever. Good. Questions, 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 questions?
So in the beginning, it was a repeating decimal, and in the end, you're just trying to find that geometric series that will give you the infinite decimal.
Here, let's step back for a second and let's look at the whole picture. I think that'll answer your question. Okay, so let's step back for a second. We originated with this guy, right? This goes on forever, an infinite decimal, and I want to come back and find out one simple fraction that gives me this whole thing. We broke it up into two pieces. The part that does not repeat is this part. Okay, that's easy to find. So we have this fraction equals 2.11, done, right? It terminates there. Okay, now this part that goes on forever, we break it up into a sum of individual decimals that each on their own terminate. So this 0.00252525252525 forever, 252525, can be thought of as an infinite sum, where the first term is 0.0025, the next term is 0.000025, right? So each one of these individually terminate. However, I want to find out the infinite sum of these individual fractions. Once we've converted each one of these individual fractions that do terminate, that's easy to convert into a fraction, then we quickly note that what we have is a geometric pattern, right? It's a geometric series where the initial term is this one, and to go from one term to the next, to the next, to the next, to the next, we would multiply by 1 over 10 squared. 1 over 100 times this equals this one. 1 over 100 times this equals this one, and so on and so forth. So it happens to be a geometric series, and we want to know the infinite sum of all of these fractions, and because it's a geometric series, then we know that it equals to this formula, right? I guess I should have also noted that in our case, the absolute value of r is less than 1. Right, the absolute value of 1 over 100, note that that is less than 1, so therefore this series, this sum applies. Right, the a was this fraction, 1 minus the r, and the r is 1 over 10 squared. And then you just do a little bit of algebra, simplify, combine, cancel, multiply numerator times the reciprocal of the denominator, and then we get to this. So this is a closed fraction such that if I divide it, it will go on forever. So I know my calculator kind of stopped, but that's not really accurate. It will go on forever and ever and ever. So what happens is if I do it the long way, if I do like long division like this, 25, you know what's going to happen? Okay, well, it goes into it 0 times, right? Put in a decimal, throw in 1 0. It goes into it 0 times, okay? Put in a decimal in there, okay? It will go into it 0 times, okay? Put in a decimal. And now 9,900 will go into 25,000. It will go into it twice. And 2 times 9,900 times 2 is 19,800, right? And then we subtract them. That's going to be 5,200, 5,200, right? And then we bring down a 0. How many times will it go into there? That's going to be 5, right? 9,900 times 5 gives you 49,500, right? So then that gets you to 2,500. Add a 0. Oh, and so you see how you end up in this pattern? You'll get a 2 there. Oops, come on. You'll get a 2 there, and then you'll get 19,800, and then you'll get the 5,2,0,0,0, and then you'll get a 5, and then you'll get a 2, and then you'll get a 5, and then you'll get a 2, and you're just stuck in this repeating pattern. Good. So this fraction gives you this decimal that repeats itself, 0, 0, and then 25, 25, 25, 25, forever. Okay, did that answer your question?
Yeah, thank you, Professor. Thank you. Yeah, it really puts it in perspective and being able to understand it.
Oh, good, good, good. Okay, we're almost done. We did the hard part. We figured out a fraction that gives us this infinite decimal. We already knew a fraction that gave you this decimal. So now the next and final steps here is to come back to here and insert our fraction that we just found. It was 25 over 9,000, 25 over 9,900, like that, gives you this decimal. So if we just add these two together, then we'll get one final fraction such that when I divide it, it gives me this result right there. Okay, common denominator, well, that's going to be easy. This is 9,900. This is 100. So if we multiply this one by 99 over 99, 99 over 99, we'll get a common denominator of 9,900. So this is going to be equal to 99 times 211 plus 25 divided by 9,900. Good. And then if we just simplify that with our calculator, 99 times 211 plus 25, I get to 20,914. 20,914 divided by 9900. So here is a fraction such that if I divide it, I will get this infinite repeating decimal. Okay. Now I know it can reduce, so if you want to go through a couple rounds of reducing it and get equivalent fractions that also work, that would be fine. Obviously, the numerator and denominator are both divisible by 2, so that could be a way for you to start reducing this. But for the purposes of my test, I wouldn't want you to go through all that trouble. You did the important part at this point, and so I would accept that answer there. But if you want to reduce it, then that's fine too. Right? Last step is to confirm it. Let's go to our calculator and divide those and confirm that we get the same answer. And did I close the calculator? I guess I did. Okay, so now just to confirm it, if we divide 20,914 divided by 9900, we get that. And again, the calculator is kind of lying to us. This goes on forever. So it's 2.1125252525. Eventually it rounded. If you try it on Excel, for example, it goes out to like 20 decimal places, and you'll see that it'll go out farther. Okay. So whatever decimal I give you, break it up into two parts. The part that has an infinite, non-repeating part, repeating part, infinite, and then one that terminates, and then take your infinite one and rewrite it as an infinite sum of fractions, identify it as a geometric series, identify the A and the R, then use the formula for the infinite sum of a geometric series to convert it into a fraction. You don't have to worry about reducing them, right? Because here you could also reduce these. 25 and 9,900 are both divisible by 5, so you could reduce it, but don't worry about reducing. Then come back and add these guys, and that's how you get your final fraction.